So I am going to call this a great success because the code ran without spitting out any errors. What we've got here is the results of this loop. So we've got minimum, aphelion, perihelion, minimum, aphelion, perihelion repeated over and over again with slightly different values. Except the minimum did come out to a consistent 1. So that might be a constant of this problem. One of the things I'm looking over as I go over the printed values is that I see that none of my values, minimum, aphelion, or perihelion, came and butted up against the very minimum or maximum values that we were looking at. So nothing went down so far as 10 to the minus 4. Nothing went as far up as 10 to the plus 3. So that's a good thing, because if we were looking in the wrong place, then it would have gone to one of those edges and stayed there. Or it might have given us a negative value, which is not terribly fun to get a negative value for r in spherical coordinates. I guess technically this is just polar coordinates, because we don't need to worry about 3 dimensions in an orbit problem, or do we? I'll need to get back to you on that. So let's see. So we've got a pretty good range of values there. So what we can do now is we can plot these things. So I can plot let's just make sure I know what my arrays are called. So I've got the power array and I've got the minimum array. Why don't we, and I've got the R-minimum, right, R-M&M array. So that's going to be pretty easy to plot. Plot power, comma, R-M&M. And that gives us a flat line as expected. We'll leave that on there for reference, just to kind of see how the rest behave. So let's add to that a plot of the aphelion. And let's see, since aphelion is farther away, let's give that one a color of green. So we'll say color equals G. I think is how you do that. Okay, yes, I did that correctly. Good job, Brian. And then what we'll do is we'll add the perihelion. And since that is the closest point, we're going to give that the color red. Okay. And everything is kind of squished together here. So we're going to turn this vertical axis into a log scale. Axis properties. So we're just logging it up today. Let's see here. So the y-axis, I want to turn onto a log scale. That shouldn't be a problem. Okay, perfect. I'm going to hit quit here. Okay, so what I notice is that let's see, so red is the perihelion, green is the aphelion. So what I notice is that they've got more or less the same kind of shape. Let's actually maximize this for now. They've got more or less the same kind of shape. It's just that one is flipped compared to the other one. Flipped is, of course, a technical term there. So that's kind of interesting. The minimum, of course, is a constant. That seems to be pretty straightforward here. And these two are each asymptotically approaching the minimum, it looks like, going to either side. So what I take that to mean is if I push this out too much farther, would you say farther or further, even though this isn't distance? If I push this out to a higher power value, then we might run into some problems, because this might try to cross the minimum. Of course, it's also possible that it does approach it asymptotically. Same thing with this one. If I head towards 0, it's not clear what'll happen. So this is some pretty interesting physics here. So I guess another way you could take a look at this would be to try to figure out what power gives you the greatest distance between your aphelion and your perihelion. That would be an interesting question to answer. So let's create an array called aphelion perihelion difference equals, now let's see here, aphelion is farther away, so I'm going to do aphi minus peri, and through the magic of MATLAB, it is going to take all of those array entries and subtract them. So it's going to treat this like an array and this like an array, and it's going to create an array here. So let's actually, let's clear this graph. I can always bring it back if I want. Plot the power, comma, aphelion perihelion difference. I wonder which one it's if there's a maximum or maybe it's a constant. That would be an interesting thing to find out. Okay, so it actually, oh, so I should have known it was going to asymptotically, it was going to behave kind of asymptotically here because, of course, that was a log scale. But I do see there's a little bit of a minimum out here. So that's interesting. Let's try zooming in on that. Is this the zoom area? Zoom area. Okay, cool. So let's zoom in from here to the end. So we do get a minimum. We get a minimum at about 1.3. So that's kind of interesting. So we live in a universe where, at least for these inputs, so that minimum location might change with these inputs. We live in a universe where if I put in those inputs, we're not at the minimum, where we would need to live in a universe with a power of about 1.3, 1.2, and and a little bit of, and just a couple cents shy of 1.3 would give you the minimum difference between aphelion and perihelion. I wonder if that's a function of these input parameters. So what I'm going to do now is I'm going to add on another little piece to the code. Let's call apdiff. Let's create that here and say that that's equal to aphi minus peri, just like we did over here, only now it's going to be part of the code. So let's do that. Let's see what we get if we run the code again. Zip. Oh, right. And of course, I need to do two things. Number one, I need to actually call this thing by the name that I gave it. And the other thing, stop that taskbar. The other thing that I need to do is I need to change these values or else I'm not going to get anything different. So this was for everybody equal to 1. Let's see what happens if we change the mass of the central object. Let's just double it. Let's see what happens. Run the code. No errors this time. Good. And let's plot power, comma, apdiff. What do we end up with? Oh, we do not get a minimum at the same location. Okay, so that is unique to the particular parameters that we selected. Is there a way I can reset the zoom? Original view. There we go. Oh, that's wonderfully helpful. Let's zoom area. Let's zoom back around this way. There's something funny going on there to the left that I might want to check out a little bit later. So actually this thing has not hit its minimum yet. Its minimum is somewhere to the right of 1.8. So why don't we try going in between there? Let's go to 1.5 and save and run. And then please plot for me power, comma, apdiff. Okay, so this is really interesting. Let's zoom, let's make the vertical a little bit easier to see there. So we're getting a minimum here, not yet seeing a minimum here, so it must be off to the right somewhere there. Let's do one more. Let's split the difference again. I just want to get a sense of how this minimum moves. Plot it. Okay, so, okay, minimum is still potentially off the screen. So this thing is rather finicky within this range that we're looking at. Let's try 1.05. Let's take smaller steps going around. All right, plot it. Show me the graph. Okay, so I've got a curve that's pretty similar to the original one, but it's already departing by a little bit, and that was just changing it by 1.05. So if I were giving this as a homework, I would ask students to create a plot of the minimum position versus the power. So there's all sorts of stuff you can do with this, or versus the power, excuse me, versus the mass of the central object. So that's one of the many things you could do with this. I suppose changing this mass is equivalent to changing this mass, or excuse me, is equivalent to changing the gravitational constant. So no sense in worrying about that one. But one thing I could do would be to also change the mass of the thing going around the sun, because that appears both in the gravitational term and in the centrifugal term. So let's actually close this out and let's get our original data set back, and we're going to plot power, comma, apdiff. We see that there's a minimum out there somewhere. Why don't we axes properties? We'll play around this for another minute or so, and then I'll probably call this episode to a rest. Let's put this one on log. Okay, so there the minimum is very visible. Yes, that is a very nice minimum there. Okay, let's see what happens when we change this thing. So we got an idea what happened when we changed capital M. The minimum shifted over to the right. Let's see what happens when we change this thing. Let's change this thing to a 0.8. And we'll run, and actually let's go ahead and put this as at the end of the code, just so I don't have to keep going back and forth doing that. All right, and run with a plot this time. So we should have 2 graphs on here. Oh, so this one we ran into a little bit of a problem. The aphelion drastically changed. So this is now butting up against that 2000 right there that we have for our leftmost R value. So apparently I needed to graph first. So changing the mass of the thing that orbits does have a drastic change on this. So it's headed, nicely down this way. So let's actually, let's bump that up a little bit more. Let's give that another couple orders of magnitude. What's a couple zeros here and there in space? Clear out our graph. Let's see if we get one that works here. Oh my, that is rather different. Oh, right. I need to set the axes to log, and that is, oh, right. Oops, that was the wrong axes. Axes properties, sorry. X, you stay linear. Y, you become log. Okay, so we're still getting the same problem there. Let's see if we can... yeah, obviously we're still getting the same problem there. Wow, this is really far out there. Maybe I should make this a little less drastic of a change. Let's see what happens here. Aphelion is still becoming way too large. We're going to give this one more try, and then I'll probably assign it as homework. If it doesn't work this time, it did not work this time, but maybe we got a little bit farther. Oh, we did get a little bit farther. Oh, and in fact, we did get a minimum, so it kind of doesn't matter what happens after here because we did get a minimum, right? So these flat lines are artifacts of the code. They are not physical, right? Because the code, I didn't set the R value up far enough. Wow, so just changing this by that much, because when we have a 1.0, we get this nice curve that does not have this little jagged part right here from the code cutting off. So just from going from 1 to 0.95, we have this change, but then this thing changes drastically on this side. So that's pretty cool. So I think I've made this episode long enough, so we will call it quits with the breaking of the code there. I'm going to load this code up onto a link in the description. Please feel free to play around with it. Let me know what you get out. See how high you can you need to get this in order to fully investigate this parameter space. This has been a fun series. We will return to space in the future to actually animate some orbits, and we'll bring this code back out to evaluate how well it's working. So thanks very much for watching. See you next time.